Up until now, we've been talking about only a description of motion. This is called kinematics. So we've described how far things have gone, how fast they've gone, and if they sped up or slowed down. Now we're going to be describing motion. This is called dynamics. And we describe motion through either energy or forces. We'll start with forces and we'll talk about energy later on in the year. Forces are a push or a pull. And there's two different categories of forces. There's contact and there's field forces. We'll start with contact forces because they're the ones that most people intuitively know, and it makes the most sense. A contact is exactly what it sounds like. It is that these two objects must be touching each other in order to exert forces. But there's lots of different contact forces, but we'll be looking at 6 of the most common ones that we'll be dealing with this year. The first force is a normal force. This is not the opposite of abnormal. Instead, it's a geometric term which means perpendicular. So if I have a surface, let's say a table, and I put a book on that surface, gravity pulls the book down, but the book doesn't fall. And the reason the book doesn't fall is because the table itself exerts an upward force to counteract gravity. That is called the normal force. Notice how it is perpendicular to the table. Now if we take this table and prop it up on one end so it's on an incline, still put that book on the table, again the table exerts a force on the book, but it's no longer upward. It is now at a slight angle, still perpendicular to that surface. Now a surface exerts more than just a normal force. It also exerts a friction force. The friction force is parallel to the surface and it opposes the motion of the object. So if I take that book and I push it to the right, the table itself is going to exert a force to the left, opposing the motion of the object. So if you have a surface and the object is being pushed or moved on that surface, there's always two forces. There's the normal force perpendicular and the frictional force which is parallel and opposing the motion. Next type of force is tension. This is a force exerted by any kind of string, rope, or cable. So if you have a child on a swing, the chains of the swing are exerting a force to support the child. That is the tension force. We could also have like a suspension bridge, and the cables of the suspension bridge are supporting the bridge itself and all the cars on it. We could also be hanging a picture, and if we hang it from a rope, the rope is exerting a tension force supporting the picture. Tension force, of course, can only pull, though. You can never push with a string. Next type of force is a spring force, and this is the force exerted by any stretched or compressed object, not just your typical spring. So it is going to be something like maybe the suspension in your car, the shocks of your car exert a force supporting your car. You could also have the spring in your pen, and that is going to be a spring force when you compress it. There's also things like a rubber band, which we don't think of as a spring, but if we stretch that rubber band, there is a spring force associated with it. Next type of force is a buoyant force, in which a fluid exerts a force on the object. A fluid is a liquid or a gas. The most common fluid we're used to is water, and whenever you're in the water, you've probably noticed that things seem a little lighter. The reason they seem lighter is because the water actually exerts an upward force on the object, helping you lift it. This is why a lot of times we do physical therapy in the water, because it's less stress on our joints. But gases exert buoyant forces as well. For instance, we're in a gas called air. And air exerts that upward force, but you usually don't notice it because our gravitational force is a lot larger than that buoyant force from the air. However, if I take a helium balloon, the buoyant force is larger than its gravitational force, and hence the helium balloon moves up and we notice that buoyant force. The last contact force we'll look at is called the applied force. It's really just a generic force for any other force not fitting one of these other categories. So if I apply a force to that book to move it across the table, it doesn't fit any of these other 5, so we just refer to it as an applied force. The next type of category is called the field forces, and these are forces that do not require contact. The most common one, but the weakest of these 4, and there are only 4 of them, sometimes referred to as universal forces as well, but this is the gravitational force we're most commonly associated with. This is an attractive force between any two objects with mass. We usually consider just the Earth. The Earth pulls things down, and that's gravity. But the Moon can pull things down. That's a gravitational force as well. But the gravitational force on the Moon is only 1/6 of what it is on the Earth. The Sun pulls things down. But it's not limited to celestial objects. For instance, if I have a calculator and a book on my desk, there's an attractive force between the calculator and the book. So why don't we notice it? Why do we not notice the book and the calculator start to move towards one another? And the reason is because the Earth is a stronger gravitational force. Because the Earth is bigger, more massive, it exerts a stronger force. And so the calculator and book are more attracted to the Earth than they are to each other. But if we were to take the Earth away and put only the calculator and book in outer space, those two objects would actually start to move towards one another because of that gravitational force. The other field forces are the electric force. This is a force between any two charged objects, like electrons and protons. If they have the same charge, like two protons, they push each other away. They repel, we say. If they are opposite charges, like an electron and a proton, they attract, meaning that they come together. We also have the magnetic force. This is between magnets, but it's the same idea. If we look at a bar magnet, it'll have two poles. It'll always have one north and one south. And if I get two north poles near each other, they are repelling. And if I have two south poles, they repel. But if I bring a north to a south pole, they attract. One of the neat things about magnets is if you ever break one in two, accidentally break one, it always forms a new north and south pole. We never have just one pole on a magnet, also referred to as a monopole. Now, they have been hypothesized that we'll eventually find these monopoles, but up until now we have never come across one in real life. The last force that is a field force is a nuclear force. This is a force between protons and neutrons, because remember, in the nucleus it's all protons and neutrons, but according to the electric force, protons push each other away. So why doesn't this nucleus break apart? Well, that's because a nuclear force brings them together. And the nuclear force and the electric force are in a constant tug of war with each other. And for most atoms, it is an even match, and they are stable. So the nuclear force and the electric force balance out, and the object is not collapsed, nor is it broken apart.